And then one of the clarification from the earlier perplex session, we were talking there about what happens if you saturate in SiO2. And someone was saying that, yes, it doesn't necessarily, when you saturate in SiO2, mean there is a H2O fluid. For example, if you were at -10 degrees C, your saturated phase would be ice. And so thinking about it in that respect. And so with that, I'll move back to Mark. And we got a couple of questions, Mark, if you're there, about paralyzer. And someone asking, I've always wondered why your discretization script is called paralyzer. And perhaps if you could give us a little explanation about it for those who missed it in the talk before I ask a couple more questions.
Sure. Firstly, I'm surprised that there's still some interest in paralyzer. I just wrote that as a little script to help me solve some problems, and it turned out I stopped developing it for years, and suddenly I find out that people are still interested. It's called paralyzer because basically what it does is it takes your problem, it splits it, your PT problem, not all of your problems, takes your PT problem, splits it into chunks, and it solves those chunks in parallel. And so if you have a computer with multiple processors in it or multiple cores in it, it can utilize all of those cores simultaneously to solve parts of the PT space, and then it recombines that program at the end. So it is kind of a somewhat low rent parallelization of perplex. I don't really have any slides prepared for it, but I can maybe, if required, if people want more information at any point, I can show some slides from an old talk that I gave.
That's fine. And so then there was another question about if you take perplex and you use paralyzer, do you know of anyone who's tried to split that up and use a supercomputer to run all of these things in parallel with each other, since some of the calculation times can be quite long sometimes for perplex? Or
yeah, it's possible. You know, if it's okay, I'm going to share my screen. I'm going to share an old slide.
Sure.
Because, and again, apologies. This is an old talk. If I can find it. Okay. So this should just explain again what paralyzer is and why and how it works. So this is a phase diagram for an average P light, and it took about 24 hours to calculate. This was years ago. So all of this is outdated. This took about 24 hours to calculate in perplex. If we look at that diagram, it needed 1265 pseudo compounds at whatever resolution I'd set to describe variation in garnet composition. It required getting on for 300,000 to describe variations in all of the minerals that are present across the entire diagram. And so essentially all paralyzer does is it thinks about this problem, splits it into smaller chunks. Of course, it doesn't know a priori how many pseudo compounds are going to be needed. Anyway, what I do here is I split this into 25 chunks. Each one of those 25 chunks, this one only needs 16 pseudo compounds to describe garnet at the same resolution. This one needs almost 13,000 to describe all of the minerals. If we look at all these, even the most complex region only needs 75,000 pseudo compounds, which is a lot less than the 300,000 for the entire box. And so essentially what paralyzer does is it splits the program up, splits the problem up, assuming this behavior that we're going to need less pseudo compounds. My computer's got 8 processors. It can solve 8 of them simultaneously. Getting to the supercomputer thing, there is a sort of diminishing returns. This is how many pseudo compounds you would need per segment. This is the 300,000 we needed originally. This is how many we would need if we broke the diagram into 100 segments. You can see that if we broke it up into 1,000 segments and solved each of them on a supercomputer, we wouldn't get back that much. In fact, we'd probably spend so much time shuffling the information between the processors that we might actually end up slowing up again. I do have somewhere. Sorry, I'm skimming through slides that I haven't opened for a very long time. Oh, the last one was what I needed. This would be the time required to solve the problem. So this 1,200 minutes, if we don't paralyze it, if we break it just into 4 sections, we go down to less than 600 minutes. If we go to 100 sections, we're about 180 or so minutes. But beyond this point, it really is diminishing returns. So maybe, I hope that answers the question.
I think that does. Yeah, no, that's really good, Mark. So since people are somewhat interested in this, somebody actually asked, how do we obtain Paralyzer? Because apparently the link is broken.
There are two problems. One, I haven't really spent any time developing it for a little while, so I'm not entirely sure how it works with the very newest version of Perplex. I can get back into that. Two, metamorphic processes at Virginia Tech website no longer exists because of things that happened here in our university. I'm writing a new website. It will be available on there. If anybody desperately needs it before then, drop me an email and I'll send it to you.
Excellent. That's great. Okay, right. Maybe I'll switch back to Doug now. Doug, we had a few questions about plot XY. Is it possible to use plot XY with other variables other variables than pressure and temperature?
I do believe so, yes. I'm kind of drawing a blank on that right now. But
that's all right.
I'm sure you can set up problems where it's not P or T. You know,
yeah,
you can set it up.
Okay, and then somebody else asking about, you had that slide with Theriac and plot XY, these phase abundances, and they were asking what determines the steepness of the transitions between the phases. And I think this is possibly more of a rock question. You were using your average water bill right there.
Yeah, the in the plot XY diagram.
Yeah, some of them are steep slopes and some of them are shallow slopes. So it's
on the diagram on the left, what you could do is you could rerun Guzzler and XPlot on the data, and you could graph in just this part. But what you can see here is that if we look at this line here, we have biotite coming up, muscovite coming down, and then they both, biotite starts going up a mode and muscovite starts going down. And if we look at the rest of the phases, we see chlorites going down there, we see starlights going down and garnets going down. And so basically you look to see what's happening. Basically what's happening, we're in a major chlorite consumption reaction. And in that chlorite consumption reaction, we're actually producing the starlight here. We're actually consuming muscovite and you're actually producing biotite. And so what happens is this reaction starts and the chlorite mode starts to go down and eventually chlorite becomes zero. Well, so there's a particular reaction that's occurring over that range and that controls the width. Now, on the other hand, this is an interesting one, the albite versus the plagioclase. We see, somebody talked about this earlier about the albite to plagioclase transition, kind of mimics the peristorite gap. And it does kind of mimic the peristorite gap at lower pressures. At higher pressures, it tends to be a very, 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 very sharp transition. And so you almost immediately lose all your albite. And so what happened is the albite went from 3 moles here, and it went all the way down to less than a half a mole in one increment here. So that's literally less than a degree or degree and a half. That's how fast the mode changed of albite, and this is how quickly the plagioclase came up. I can't give you the technical reason on why that one is so abrupt there. I think it's not really modeling a miscibility gap appropriately. That's not what it's doing. It just happens to work out that you can get albite and plagioclase coexisting with one another. So it's really, you see these reactions start and they'll continue until some other mode becomes zero. And sometimes that reaction occurs over 2 degrees, sometimes it occurs over 10 degrees, and sometimes it occurs like this over 100 degrees.
No, I think that's a great answer here. Okay, maybe we'll flick back from Mark. We've still got a few minutes left. Somebody here asking Mark, what are the best practices on the user side to follow while you're excluding phases in Perplex?
That's a great question. I would say the thing that I would do is to start by not excluding any phases. Let all of the phases that are in the thermodynamic data set, fight with each other for stability. Don't exclude any phases initially. And then if you see that in the diagram, things are going a little awry, you might want to think then about excluding those phases. B, you've maybe learned something about how the data set works, and C, you've got sort of more food for thought. So basically, I would start by not excluding anything. Have a look at the result. It's an iterative process. I mean, I showed you a diagram. I said, oh, this took 35 seconds to calculate or whatever it was. In practice, to go from having a problem that you want to solve to actually having the problem resolved, it's never 35 seconds because you never just do one calculation. You need a little bit of iteration along the way.
Excellent. So I suppose I could ask Doug the same question from a Theriac domino point of view. Run everything, would you say, or run the files as downloaded? I'll let you answer that.
Well, I'm a little more conservative, I guess. I tend not to run all the phases in the database. And it might be, I started off as a thermocalc user, and it seems to be in the thermocalc world, you have to add what phases you want to consider. And so you think about it, okay, what phases should be stable here? And you add those up. And I guess I kind of continued to follow that approach. I have been burned sometimes where I didn't have some stuff activated I should have had activated, and I missed some stuff. I mean, it's happened for sure. On the other hand, you do run across phases, like particularly some of these new high pressure phases in the Holland Powell database. And if you leave those active as pure phases, you'll find that you can predict them stable 3 kilobars, 340 degrees C. And it's messing up your phase relations. It shouldn't be there. That could be for a variety of reasons. It could be you're not considering a solid solution model at low pressure conditions that you should be. And had you been considering a specific solid solution model at low pressures, then that high pressure phase would have never been stable in the first place. And so that happens, and it happens probably more frequently than you think. It happened to me on one of the diagrams I produced here. I had microcline on, I had it activated so that at the low temperature end, what I was trying to do was go down to pretty low temperatures in the metapolitic system and have microcline stable at low temperatures, and then see how that impacts the reacting in of biotite. So I was trying to get biotite not to be stable down at 200 degrees. And I left that on, and then by the time I got up to 640 degrees C and 1 kilobar, I'd hoped my ternary feldspar solution model would be stable, and I'd get a K feldspar rich ternary feldspar coexisting with plagioclase rich ternary feldspar, but I didn't. Instead, I got a ternary rich plagioclase feldspar coexisting with pure microcline. And that's a case where I need to turn off the microcline because I have sanidine as my end member in my my ternary feldspar model, and the bulk system composition was just such that that solid solution effect wasn't enough to stabilize the ternary solid solution with sanidine over pure microcline. So there are times when you need to turn some of the stuff off.
That's great. Thanks, Doug. I think, with those two answers from Mark and Doug, that's a good place to end the this open Q&A.